For the first time, scientists have discovered a particle that has no mass moving in one direction, but gains mass when moving in another. This particle, called a semi-Dirac fermion, was first theorized to exist over 16 years ago, but has only now been observed in a crystal of a material called zirconium silicon sulfide, a type of semi-metal. This groundbreaking discovery opens up exciting possibilities for future technologies, including advances in batteries, sensors, and even quantum devices, according to researchers from Penn State and Columbia University. So how does this work? Normally, particles have mass because of how they interact with other forces. But some, like photons, particles of light, are massless because all of their energy comes from their motion. They travel at the speed of light, and according to Einstein's theory of special relativity, anything moving at that speed can't have mass. In solid materials, though, particles don't always behave the way they do in free space. Instead, the interactions of many particles can create quasi-particles with unique properties. Semi-Dirac fermions are a perfect example. They act massless in one direction, but have mass when moving in another. Scientists first theorized their existences back in 2008 and 2009, but it wasn't until now that they've been spotted. The discovery happened somewhat by accident. Researchers were studying the properties of zirconium silicon sulfide using a technique called magneto-optical spectroscopy. This involves shining infrared light on a material while applying a powerful magnetic field and analyzing the light that reflects back. They weren't looking for semi-Dirac fermions specifically, but the data revealed patterns that fit their predicted behavior. Here's where it gets even more fascinating. When a strong magnetic field is applied to a material, electrons inside of it occupy specific energy levels, known as Landau levels. These levels are like steps on a staircase. They're fixed, and their spacing depends on the electron's mass. But in zirconium silicon sulfide, something unexpected happened. The levels didn't behave as they should, revealing a key signature of semi-Dirac fermions, known as the B to the 2/3 power law. The experiments were conducted at the National High Magnetic Field Laboratory in Florida, home to the world's most powerful sustained magnetic field, 900,000 times stronger than the Earth's magnetic field. Researchers cooled the zirconium silicon sulfide crystal to an incredibly low temperature, just above absolute zero, and observed how electrons responded to magnetic field and light. What they found was astonishing. The electrons inside the material seemed to lose their mass entirely when moving in a straight line, behaving like pure energy moving at light speed. But when they changed direction, they gained mass and experienced resistance. Imagine a train speeding along a straight track. It's fast and unimpeded. But when it reaches an intersection and switches to a perpendicular track, it slows down and encounters friction. That's essentially what's happening here, except on the quantum level. Zirconium silicon sulfide, like graphite, is a layered material. If scientists can isolate single layers, much like how graphene is derived from graphite, they might be able to harness the unique properties of semi-Dirac fermions. This could lead to innovations in everything from energy storage to advanced sensors. But the most exciting part? There's still so much we don't understand. The data from these experiments revealed things that current theories can't fully explain. Researchers are now looking further to uncover what's really happening at the quantum level. Who knows? Just like with graphene, semi-Dirac fermions in zirconium silicon sulfide might just be the next big breakthrough in material science. Now, thank you for watching, and as always, have a Voltastik day.